Interstellar Comet 3I/Atlas has already begun its long journey out of the solar system. Yet even as it recedes from Earth, it continues to reshape scientists' understanding of how small bodies behave beyond their native stellar environments. Detected as a rare visitor from another star system, 3I/Atlas quickly drew the attention of astronomers around the world, not only because of its interstellar origin, but because of the unusual and dynamic behavior revealed as it interacted with the Sun. Detailed observations have shown that this object is far from a passive, frozen relic drifting through space. Instead, it is an active and evolving body whose behavior provides a rare window into the physical properties of material formed around another star. Comets are typically characterized by their bright comets and long tails, created when solar radiation heats their icy nuclei and causes gas and dust to stream outward. In most cases, these tails point away from the Sun, pushed outward by solar radiation pressure and the solar wind. However, 3I/Atlas displayed something far more unusual: a sun-facing anti-tail. While anti-tails are rare, they are not entirely unprecedented among comets originating within our own solar system. What makes 3I/Atlas exceptional is that this phenomenon was observed in an interstellar comet for the first time, offering astronomers a unique opportunity to compare the physical behavior of extrasolar material with that of native solar system bodies. One of the most striking discoveries associated with 3I/Atlas was the detection of jet-like structures embedded within its anti-tail. These jets, composed of dust and gas released from localized regions on the comet's surface, were observed to extend enormous distances, in some estimates reaching up to 1 million kilometers in length. Even more intriguing was the fact that these jets did not remain static. Instead, they exhibited a periodic wobbling motion, repeating every 7 hours and 45 minutes. Such behavior strongly suggested that the comet's nucleus was rotating, causing active regions on its surface to sweep through space like the beam of a cosmic lighthouse. Through careful analysis of this wobbling motion, researchers were able to infer the rotation period of 3I/Atlas. Their findings indicated that the comet completes a full rotation roughly every 15 hours and 30 minutes. This was a significant revision compared to earlier estimates, highlighting how continued observation can dramatically refine scientific understanding. Rotation rates are a critical parameter for comets, as they influence everything from surface activity to structural stability. A faster rotation can increase stress on the nucleus, potentially leading to fragmentation, while also affecting how heat is distributed across the surface. The observations that led to these insights were made over an extended campaign spanning 37 nights between early July and early September of 2025. Using the 2-meter twin telescope at the Tide Observatory in Tenerife, astronomers were able to track subtle changes in the comet's coma and tail structure as it approached the Sun. Early in the observation period, the coma appeared as a diffuse, sun-facing fan of dust. As weeks passed and solar influence intensified, this structure gradually evolved into a more pronounced anti-solar tail, illustrating how rapidly cometary features can respond to changing environmental conditions. This transformation was driven largely by the increasing impact of solar radiation on the dust particles surrounding the comet. As 3I/Atlas moved closer to the Sun, reaching a distance of about 210 million kilometers, at its closest approach in late October 2025, sunlight exerted greater pressure on smaller dust grains, reshaping the coma and tail. The appearance of the anti-tail and its embedded jets during this period reflects a delicate balance between the comet's intrinsic activity and the external forces acting upon it. What sets 3I/Atlas apart from earlier interstellar visitors is the level of detail with which its activity has been characterized. The first known interstellar object, Oumuamua, discovered in 2017, showed no obvious coma or tail, leaving scientists to debate its true nature. The second, 2I/Borisov, clearly behaved like a conventional comet, complete with gas emissions and dust production. 3I/Atlas builds upon these discoveries by revealing complex jet activity and rotational dynamics, demonstrating that interstellar comets can be just as diverse and active as those formed within our own solar system. The detection of wobbling jets in the anti-tail is particularly valuable because it provides clues about the internal structure and composition of the comet. Jets are thought to originate from localized patches of volatile material on the nucleus, where subsurface ices are exposed to sunlight and rapidly sublimate. The regularity of the wobble suggests that these active regions are relatively stable over time, and that the nucleus itself is coherent enough to sustain repeated cycles of activity without breaking apart. From a broader perspective, studying objects like 3I/Atlas allows scientists to test whether the processes that shape comets are universal or specific to our own solar system. If interstellar comets exhibit similar behaviors, such as jet formation, rotation-driven modulation of activity, and the development of anti-tails, it implies that the physical and chemical processes governing small icy bodies are widespread throughout the galaxy. Conversely, any differences can reveal how varying stellar environments influence the formation and evolution of planetary debris. The findings related to 3I/Atlas were shared with the scientific community through a paper published on the preprint repository AR14. In their analysis, the researchers emphasized that observing outgassing and jet behavior in an interstellar comet represents a rare scientific opportunity. Unlike solar system comets, which have undergone repeated passages near the Sun and extensive thermal processing, 3I/Atlas is considered relatively pristine. Its material likely remained cold and unaltered for billions of years before its brief encounter with our star, preserving a record of conditions in another planetary system. As 3I/Atlas now fades into the depths of interstellar space, the data collected during its passage will continue to be analyzed for years to come. Each new insight contributes to a growing understanding of how common such visitors might be, and what they can tell us about the formation of planets around other stars. While only 3 interstellar objects have been confirmed so far, advances in survey technology suggest that many more await discovery. In the end, 3I/Atlas serves as a reminder that the solar system is not an isolated island in space, but part of a dynamic galactic environment where material is constantly exchanged between stars. The wobbling jets, the rare anti-tail, and the refined measurement of its rotation period all underscore how much can be learned from even a brief encounter with a wandering comet. Long after it has vanished from our telescopes, 3I/Atlas will remain a key reference point in the study of interstellar visitors, expanding our understanding of the cosmos and our place within it.